Hi all, welcome to Go Classes. So let's start the solution session for today's DPP. Today we have digital logic subject DPP. So let's start. Did you try all these questions by yourself? Audio, video, volume, echo, everything is perfect. Everything is fine. Let me know. Then let's start this session. Hi all, welcome to Go Classes. Welcome to Go Classes Gate CS YouTube DPP series, and today's DPP is subject is digital logic. The topic is minimum NAND NOR implementation. Minimum number of two input NAND gates, two input NOR gates required to implement a Boolean function. And all the questions are taken from Purdue University. Let me tell you that the Go Classes YouTube DPP series for Gate CS, in short, GOT DPP series. The complete playlist link you can find in the description, also in the pinned comment. All the questions in our DPP series will be taken from the standard resources to ensure that you practice top quality questions. So you can search on YouTube Gate CS DPP. This is what you need to search. Just search it, and then you can see this Go Classes GOT DPP series, or I can say Gate CS YouTube DPP series. This type of videos will be shown to you on YouTube. And here you can notice one thing here, that here is the link of the playlist. You can see Gate CS GOT DPP series playlist, and this is the link. Okay, so you can check it out. Now let's start. Let's solve these questions from Purdue University. Total 4 questions are there. You can see the following K-map applies to the questions on this quiz. This K-map is given to us. Based on this K-map, there are total 4 questions that we need to solve. Let's see the first question. The first question is asking the cost of minimal sum of product realization of this function, assuming both true and complemented variables are available. And what is the question number 2? That is the cost of minimal product of some realization of this function, assuming true and complemented variables are available. These 2 questions are similar to each other. One is asking for cost of minimal sum of product, and another is asking for cost of minimal product of sum. And you can see the question 3 and 4, they are also similar to each other. You can see question 3 is asking, assuming the availability of only true input variables, the minimum number of two input NAND gates required to realize this function. And in the question number 4, it is asking the minimum number of two input NOR gates. So here you can notice in the question 1 2 are similar, and question 3 4 are similar. So let's solve these questions. First we will discuss question 1 and 2. One thing I want to know, what is the meaning of the cost of minimal sum of product realization of this function? What is the meaning of this statement? Tell me. In the question number 1, it is asking the cost of minimal SOP realization of this function where both true and complemented variables are available. Means complemented variables are directly available. You don't have to generate them. You don't need inverter to generate complemented variables. That is given to you. Both true and complemented variables are already available. You don't need inverter to generate the complemented variable. Similarly, you can see in the question number 2, it is asking the cost of minimal POS realization of this function. Again, the true and complemented variables are available. So to generate the complemented variable, we don't need inverter or NOT gate. Now the question is simple. Is it asking the total number of literals? What is the meaning of cost of minimal SOP? What is the meaning of cost of minimal POS? What do you think? Let me know in the chat. Is it asking the number of literals, or is it asking for number of total number of logic gates? What is the meaning of cost of minimal SOP realization and cost of minimal POS realization? Think about it and tell me what is the meaning here. Is it asking for total number of literals? Is it asking for total number of logic gates? What it is asking? First, you understand that. Okay, so here, let me tell you what it is asking. Okay, just wait. So basically, these are the question 1 and 2, and you can see these two questions. They are asking for cost of minimal SOP realization, cost of minimal POS realization. So what is the meaning here? Let me tell you. This is the screenshot from Charles Roth book. This is a digital logic design book by Charles Roth, and you can see here it is given to you what is the meaning of cost. You can see here cost. So let's see what this says. You can see when a function is realized using and or gates, means when a function is in the SOP form or POS form. So you can see when a function is realized, when we realize a function, when a function is realized using and or gates, the cost of realization. What is the cost of realization? The cost of realization is the summation of the number of logic gates and the number of gate inputs. This is the answer. Okay, so very simple point. When a function is realized using and or gates and comma or gates, then remember the cost of realization, that is related to, or I can say that is summation of the number of logic gates plus the number of gate inputs. Okay, here you can see, therefore, to find minimal cost two level and or circuit, we will find minimum expression in sum of product or product of sum. So basically what you do, to find minimum cost of realization using and or gates, you find minimal SOP, you find minimal POS, and then you see how many total logic gates will be required and how many gate inputs are there, and you do the summation. That will be your answer. Is this clear? So here you can see I have written here, this is the concept used in this question. Now some of you might be thinking that you did not know about it. That's fine, don't worry. You can never become perfect. Okay, life is all about learning. So you can say that, okay, from this question, or I can say from this session, you got to learn something new. Okay, I hope you are getting my point. Many of you might be thinking that, sir, I did not know about it, I did not know about this point. So that is the reason I am telling you that in this session you got to learn something new. That's it. That's important, right? Okay, life is all about learning. You can never become perfect, you can never have the perfect knowledge. Okay, so I hope you understood this point, that here the question is asking, you can see in the part 1 part 2, the question is asking the cost of minimal SOP realization and the cost of minimal POS realization. And I am just telling you the concept. Here you can see when a function is realized using and gates and or gates, then the cost of realization is basically summation of the number of logic gates and the number of gate inputs. You just do the summation. Okay, very simple. Now let's solve this question. So let's see the part 1. In the part 1, it is asking the cost of minimal SOP realization. So first we will find the minimal SOP expression from this K map, and then we will see how many logic gates are required and what is the total number of gate inputs. Then for the part B, we will find the minimal POS expression, and then we will see, to realize it, how many logic gates will be required and what is the total number of gate inputs, right? Okay, very simple, right? So let's see the part 1 first. First we are looking at part 1. So for that we will find the minimal SOP. Let's find minimal SOP expression. So to find minimal SOP expression, what we are going to do? We are going to cover all the 1 cells, right? Here you can see these are the 1 cells. We need to cover all the 1 cells with minimum number of cubes, every cube as large as possible. And remember, we don't care about don't care. don't care, we may cover or we may not cover. Basically, if you are getting a bigger cube by using don't cares, then you can use don't cares. Otherwise, you don't have to worry about the don't cares. Okay, the point is to find the minimal SOP from the K-map, we just need to cover all the one cells with minimum number of cubes and every cube as large as possible. So let's see. So to cover these two ones, you can see that I can make this 4 size cube. I want to make cubes as large as possible and minimum number of cubes I want to use. Then I will get minimal SOP. Okay. Next, you can see now these two ones have been covered. This one is remaining. So you can see from this one cell point of view, you can see this is a useless neighbor because these are 0 cells. These are useless neighbors. You can see this is the only useful neighbor because I can fold the KMF horizontally, vertically, right? Yes or no? So you can see here, this one cell has this useful neighbor. So what this one cell can do, it can use this useful neighbor and it can make a cube. So you can see this cube also we will get. That's it. We have covered all the one cells with cubes as large as possible and minimum number of cubes. That's it. So now let's see what will be the product term corresponding to this pink cube. So this pink cube, this is in the area X. Okay. You can see this is in the area X. That's it. So you can see that this pink cube, for this pink cube, the product term is basically X. Now let's see what about this orange cube. What is the product term corresponding to this orange cube? You can see this orange cube, this is in the area Y bar, also in the area Z bar, Y bar, Z bar. So what is the minimal SOP? The minimal SOP expression that I got, that is X or Y bar, Z bar. Okay. Now remember, in the part one, it is asking the cost of minimal SOP realization. It is asking the cost of minimal SOP realization. So this part one is not asking for number of literals. Okay. It is asking for the cost of minimal SOP realization. And here you can see it is given to you that both true and complemented variables are available. So to get complemented variable, you don't need inverter. Okay. So already you have complemented variables available to you. So let's see what will be the cost of realization. For that, cost of minimal SOP realization, for that what you will do, you will find minimal SOP and then you will find the AND OR circuit. Okay, so let's see here what AND OR circuit I will get. So here now let's see the realization. Okay, so let's see in the realization, you can see that, notice one thing, I already have Y bar. Okay, I don't need inverter. Don't do like this. I already have Y bar. You can see, you can read this, that assuming both true and complemented variables are already available to you. So remember, we just need AND gate. We need AND gate. Y bar, Z bar are already available to us. Okay, so you can see we got Y bar, Z bar. Then what I need to do? Assume this Y bar, Z bar is alpha. So I need X or alpha. So I need OR gate. And that's it. So tell me, what is the cost of realization? What is the cost here? Here, tell me what is the cost? The cost is basically the number of logic gates 2 plus the number of gate inputs. You can see this is a input, gate input. So total 4 gate inputs. So the cost is basically 6. I hope you understood. Okay, is this clear? So very simple, remember, the cost of minimal SOP realization, that is equal to the number of gates plus the number of inputs, gate inputs. Okay, that's it. Very simple. I hope you understood this. So the answer will be 6 for this part 1. Okay, the answer is going to be 6. Now let's see the part B. The part B is asking the cost of minimal POS realization, and the true and complemented variables are already available to us. So what we will do, we will find minimal POS expression, right? So let's find the minimal POS now. To find the minimal POS expression from the K-map, what we are going to do, we will cover all the zero cells with minimum number of cubes, every cube as large as possible. Notice one thing, because we are finding minimal POS, so here let's label the K-map. Here it will become X bar, it will become Y bar, it will become Z bar. Correct? Yes or no? Okay, yes. Very simple. So this is the point. Because now remember we are finding minimal POS. So when you are finding minimal POS, this is how you will label the K-map. Now you can see this is the X bar area, so this is the X area. You can see this is the Z bar area, so this is the Z area. This is the Y bar area, so you can see this is the Y area. Okay, now let's cover all the zero cells with minimum number of cubes, every cube as large as possible. Okay, so here you can see these three zeros I need to cover. Let's look at this zero. You can see from this zero point of view, this is a useless neighbor because this is one cell. This is a useless neighbor, this is a one cell. There is only one useful neighbor, this. Correct? So you can see with help of useful neighbor, this cube I can create. Now these two zeros we have covered. I need to cover this zero also with minimum number of cubes and every cube as large as possible. And remember, I don't care about the don't cares. It is not necessary to cover all the don't cares, right? So here you can see to cover this zero, can I make 4 size cube? No, I cannot make 4 size cube. I cannot make. Remember, either you can either you can do like this or you can do like this. Both are fine. Both are perfectly fine. Either you can do like this, or or you can or you can do like this. Okay, both are perfectly fine. Is this clear? So remember, we are getting two minimal POS. Basically, we are getting two minimal POS expressions. Okay, what are the two minimal POS expression you can see? Let's see minimal POS 1. The minimal POS 1 expression here, let's write the sum term. Okay, for these cubes covering zero cells, let's write the sum term. So you can see what is the sum term corresponding to this orange cube. This is in the area X, also in the area Z bar. So you can see the sum term will be X or Z bar. For this green cube, what is the sum term? This is in the area Y bar, also in the area Z. So you can see Y bar or Z. So the minimal POS 1 means there are two minimal POS expressions. So one of them is basically X or Z bar and Z or Y bar. Okay, yes or no? Very simple. Now let's see the cost of realization here. The realization, let's see. So you can see we need AND gate for these two. But here you can see, remember Z bar is already available to us. Y bar is already available to us. So for X or Z bar, what I need to do? I need OR gate. This OR gate I need for X or Z bar. Okay. Another OR gate I need. Another OR gate I need for Z or Y bar. Correct. And then AND gate I need for this. Okay, that's it. So tell me how many gates we are using? 3. And how many inputs? How many gate inputs? 1, 2, 3, 4. Then you can see 5 and 6. So tell me what will be the cost? The cost will be 3 plus 6. The answer will be 9. I hope you understood this. Okay. Remember, you can find the minimal POS 2 also. If you want, you can find minimal POS 2 also. There is another minimal POS expression possible. If we do grouping like this, okay, then let's see here. What is the sum term corresponding to this orange cube? So this is in the area X, also in the area Z bar. So X or Z bar. What about this pink cube? What is the sum term corresponding to this pink cube? This is in the area X, also in the area Y bar, X or Y bar. Okay, so you can see minimal POS expression. Another minimal POS expression that we got, because basically we have two minimal POS. Okay, so that is X or Y bar and X or Z bar, right? Now here also you can check what will be the realization. The realization will be, I need OR gate for X or Y bar. Y bar is already available to us. Okay, that is given in the question, that true variables and complemented variables are already available to us. We don't need to generate them using the inverter. Okay. Next, you can see that Z bar is already available to us, and here this X. Okay, and you can see this AND gate. Now, so tell me total, what is the cost? Cost of minimal POS realization. So the total number of logic gates, that is 3 plus. What is the total number of gate inputs? You can see. Look from the gate point of view. Gate inputs. Look from the gate point of view. 1, 2, 3, 4, 5, 6. Total 6 gate inputs are there. So again, the answer is 9. Okay. So whether you consider this minimal POS expression or you consider this minimal POS expression, you can see the cost of minimal POS realization will be same, 9. Okay. So here for this question, the answer will be here, option E. I hope you understood this. Is it clear to everyone? The concept I have already covered here. You can see, okay, this concept. So basically, when a function is realized using AND gates or gates, then the cost of realization is the summation of the total number of gates and number of gate inputs. Okay, just do the summation. I hope it is clear. So the cost of minimal SOP realization, the cost of minimal SOP realization, for that you will find the minimal SOP expression. The cost of minimal POS realization, for that you will find minimal POS expression. And then you can implement with help of AND gate or gate. Then you can check what is the total number of logic gates and what is the total number of gate inputs, and you do the summation. That is your answer. Okay. I hope you understood this point. So for the first question, for the second question, the answers are, you can see, B, E respectively. Let me show you the answer given by the Purdue University. You can see this is the official answer given by the Purdue University also. Okay, here you can notice that this is the minimal SOP expression. This is the minimal POS expression. You can notice, you can check it. This is the minimal SOP expression. This is the minimal POS expression. Then you can see the cost of minimal SOP realization. That is, you can see here 4 inputs, 4 gate inputs, and 2 logic gates. So the answer is 6 for the first part. And you can easily notice the second part. The cost of minimal POS realization, that is, you can see 6 gate inputs, 3 logic gates. So the answer is basically option E. Okay. I hope you understood. So this is the official answer given by the Purdue University. Okay. Let's solve the third part now. But before that, you tell me, did you understand the analysis so far? Let me know. Please tell me. Let me know. Did you understand so far whatever we have seen? Okay. Let's solve the part 3. Assuming the availability of only true input variables, means now the complemented variables are not available to us. To generate the complemented variable, we need to generate it. It is not by default available to us. It is not directly available to us, right? Okay. So here you can see, assuming the availability of only true input variables, the minimum number of 2 input NAND gates required to realize the function is. So the expression we have already found for the function. What was the expression? The expression was X or Y bar Z bar. Correct? This expression we have already found. You can see X or Y bar Z bar from the given K map. So we have this expression, X or Y bar Z bar. Now you can see this is a SOP expression. Correct? This is minimal SOP expression. Now Do you recall in the Go classes lectures where we were discussing the minimum NAND implementation, minimum NOR implementation? In a very detailed way, we have discussed the minimum NAND implementation, minimum NOR implementation. I told you some guidelines were there. Okay, all the standard Boolean functions we have seen, all the standard logic circuits we have seen, all the guidelines we have seen, a lot of practice we have done. So, do you recall when the question asks you for minimum NAND implementation, then the step number one in the guidelines, the step number one is you find the minimal SOP expression. Okay, so we have the minimal SOP expression. What was the step number two? The step number two was you write this F equal to F double complement. Yes or no? This F you write F double complement, because remember when I do double complement, it does not affect anything. It does not change F. So F I can write F double complement. So here you can see this X or Y bar Z bar. I can do double complement, means complement then again complement. Okay. Now this inside complement, let's apply the De Morgan law. So if you apply the De Morgan theorem, then I will get X bar and what I will get here, Y bar Z bar whole bar. Correct. Okay. Then you can see whole complement. Yes or no? This is what I will get. Very simple. Now you can notice for X bar, I need one NAND gate. Yes or no? Let's find how many two input NAND gates are required. So one NAND gate I need here. Okay, because remember the question is saying that assume the availability of only two input variables. Means X bar is not available to me. I need to generate X bar. To generate X bar, I need one NAND gate. One two input NAND gate I need. Okay, yes or no? This type of two input NAND gate I need. This two input NAND gate will give me X bar. Okay, so very simple here. One two input NAND gate I need here. Next, you can see for this Y bar, one more I need. For this Z bar, one more I need. Now notice, assume this Y bar is alpha, assume this Z bar is beta. Then for alpha beta whole bar, I need only one, because that is the NAND equation. What is the NAND expression? You already know NAND expression, that is basically alpha beta whole complement. This is called NAND expression. First you do AND, then you do complement. Correct? So here, very easy point that for this Y bar, one NAND gate, for this Z bar, one NAND gate. But then this is alpha, this is beta. Alpha and beta whole complement. For this whole thing, one more NAND gate. Then you can see, let's assume this is alpha and this whole thing is beta. Alpha and beta whole complement, one more NAND gate. Here, one more NAND gate. So total how many NAND gates? Total 5. So total 5 two input NAND gates we need. Is this clear? So you can see the answer for this question will be option A, that is 5. One more thing. I told you in the Go classes lectures, I told you one thing very clearly, that to find the minimum NAND implementation, to find the minimum NOR implementation, there is no systematic procedure which can always give you the guarantee of minimum number of NAND gates, minimum number of NOR gates. Okay, if someone is telling you that there is a procedure, there is a systematic algorithm, there is a procedure, okay, that these are the guidelines, if you follow them, then 100% you will get minimum number of NAND gates, minimum number of NOR gates, then they are lying to you, because there is no such procedure existing in the whole world. Okay, so remember, this type of questions are basically hit and trial questions. Okay, but most of the time, if some standard Boolean function is given to you, then those we have seen in the lectures, most of the time they will ask you standard Boolean functions. If they ask you standard logic circuit, for example, half adder, full adder, binary adder, 4-bit binary adder, n-bit binary adder, multiplexer, or if they ask you, some other standard logic circuit, then those also we have covered in our Go classes lectures. Correct? Now, if non-standard Boolean function is given to you, then we have seen the guidelines. You can apply the guidelines. This all we have seen, but still remember, there is no guarantee that for a random Boolean function, you can, the guidelines can give you 100% guarantee of minimum number of NAND gates or minimum number of NOR gates. So what to do? I told you in the DPP day 2 session also, I told you this point, that you can think, you know if you can think something smart, And if you can do it, if you can do the realization with less number of gates, then that will be your answer. Okay, so you look at the expression, and after looking at the expression, then you think, can you think something smart? If you are not able to think something smart, then just follow the guidelines and get the answer. Most of the time in the gate exam, all the questions that have been asked, you can solve using the guidelines, or the standard functions they will ask, or the standard logic circuit they will ask. Half adder, full adder, multiplexer, n bit binary adder. Okay, these are some standard logic circuits that they can ask. Okay, so I hope this point is clear. So here, let's see that the answer we got that is 5 NAND gates, 5 2 input NAND gates. But can we do something smart here? Let's check. Okay, let's check. Here, using the guidelines, this is using the guidelines. So you can see, using our guidelines, this is the answer we got. Using our guidelines, we got minimum number of 2 input NAND gates. Minimum number of 2 input NAND gates required, that is 5. Okay, now you might be thinking, sir, I can do maybe something different. For example, this expression is given x or y bar z bar. Now notice one thing, this is not NAND equation. Yes or no? NAND expression is different. NAND expression is basically alpha and beta whole complement, or you can say alpha complement or beta complement. Okay, so remember, this is NAND expression, this is NAND expression, this is not NAND expression. Okay, now let's assume someone is thinking like this, that okay, sir, for z complement I need one NAND gate, for y complement I need one NAND gate, then for this AND operation we need two NAND gate, because we already know for alpha and beta we need two NAND gates. Okay, then here you can see total 3 NAND gates so far. Total 3 NAND gates. Now you can see what we have here, x or alpha. Now here what we have x or alpha. For a moment, let's assume this is alpha. Then for x or alpha, for OR operation, how many NAND gates we need? How many 2 input NAND gates we need? 3. 3 NAND gates we need here. So if you think like this, then what is the answer you are getting? By this method, you are getting the number of 2 input NAND gates required, that is 1 plus 1. You can see 2 plus 2, 4 plus 3, 7. This method is giving you 7 2 input NAND gates. Correct? If you do like this, then you will get 7 2 input NAND gates. So tell me, this 7 is less or this 5 is less? 5 is less, so the answer will be 5. I hope you understood. And remember, using our guidelines, we are getting 5. And if you directly do, then you are getting 7. Then of course, using our guidelines, we are getting 5, so that will be the answer. Okay, is this clear? Simple point. So here the answer will be 5. So definitely this is not minimum. This is not minimum. Okay, I hope you understood. So for this question, you can see the answer will be option A. Simple point. Okay, now let's see the next. This is the fourth part. Assuming the availability of only true input variables, means the complemented variables are not available to us, the minimum number of 2 input NOR gates required to realize the function. What is the function expression? The function expression is x or y bar z bar. This is the function expression. Okay, correct. Now let's see what will be the answer. Now first, let's apply the guidelines. This is going to be an interesting question. It will show you something, okay, which can help you. So you can see that this is the expression. Now first, let's apply our guidelines. Okay, let's see. First, let me apply the guidelines. Using the guidelines, let's see what answer we get using our guidelines. Okay, then we will see whether it is minimum or not. But let's start with our guidelines. In our guidelines, I told you that when the question asks you for minimum NOR implementation, then first you find the minimal POS form. This is minimal SOP form. And using our guidelines, what is the step number one? The step number one is that you find the minimal POS form. That also we have already found. If you notice, the minimal POS form we have already found X or Y bar and X or Z bar. Correct? Okay, so remember the minimal POS form we have already found X or Y bar and X or Z bar. Okay, so this is the minimal POS form now. So this is the step number one. What was the step number two in our guidelines? That you write F equal to F double complement. So let's write F equal to F double complement. So you can see X or Y bar and X or Z bar. Whole complement, whole complement. Correct? Okay. Now here you can just apply the De Morgan law. So what we will get, you can see we got F equal to, if we apply the De Morgan law, we will get X or Y bar whole bar. Correct? Or X or Z bar whole bar. And then remember there is another complement outside. Okay. So here you can see we are applying the De Morgan law. So we are getting X or Y bar whole complement or X or Z bar whole complement, and there is outside complement. Very simple. Now here you can notice one thing. Complemented variables are not available to us. So you can see for Y bar we need one NOR gate. For Z bar we need one NOR gate. Two NOR gates so far. Then you can see what is the NOR equation. The NOR expression. The NOR expression is basically alpha or beta whole complement, or I can say alpha complement and beta complement. So remember that this is NOR expression, this is NOR expression. So here you can see for Y bar I need one NOR gate, for Z bar I need one NOR gate. Then you can see if I assume this Y bar is alpha, then X or alpha whole complement, this is NOR equation. So one more here. Here you can see if I assume this Z bar is alpha, then X or alpha whole complement. Here I need one more NOR gate. Then if I assume this is alpha, this is beta, then alpha or beta whole complement, that is NOR equation. So for that one more. Tell me, according to our guidelines, how many NOR gates you are getting? So you can see that 5 NOR gates we are getting. 5 to input NOR gates needed. Yes or no? So using our guidelines, we are getting this value 5. But remember, I told you that there is no guidelines, there is no systematic procedure which can always give you the guarantee of minimum number of NAND gates or minimum number of NOR gates, right? So our guidelines will help you most of the time. But our guidelines also cannot help you all the time, because there is no algorithm in the whole world. There is no algorithm, there is no systematic procedure existing which can, always give you the guarantee of minimum number of NOR gates or NAND gates. So here we have this value 5. One thing is certain, that the answer will not be bigger than 5. Yes or no? The answer will be either 5 or less than 5. Okay, so you can see using our guidelines, we got the value 5. But here something smart actually you can do. What is something smart that you can do? Our expression, our f is equal to X or Y bar Z bar, right? This is f. Can you see something here? Can you see something in this expression? Yes, you can see already this is NOR expression. Yes or no? See, you can already see that there is NOR expression in our function. Already there is NOR expression. You don't have to think too much. What is NOR expression? NOR expression means alpha or beta whole complement, or I can say that alpha complement and beta complement. This is NOR expression, this is NOR expression. And remember, for a NOR expression, I need only one NOR gate. I only need one NOR gate for NOR expression. Okay, so here you can think, you can be smart. You don't have to apply the guidelines. Just look at the function. And here you can see, look at the expression here. This is NOR equation. This is NOR expression. For this NOR expression, I need only one NOR gate. Only one NOR gate I need for this NOR expression, Y, Z, and that's it. You got your Y bar, Z bar. Only one NOR gate I need. Then you can see, now let's assume that this is M for a moment. Then tell me, for X or M, how many NOR gates will be required? X or M. For X or M, for OR operation, how many NOR gates are required? Two NOR gates required. Yes or no? Here, two NOR gates required. So you can see that this is basically M. We are assuming that this is M. Then you can see for X or M, you need two NOR gates like this. This is X, okay, like this. And that's it. This is your F. So finally, the answer will be what? Three NOR gates are required. Yes or no? Okay, so I can say that here you can see that three NOR gates required. Three two input NOR gates required. And this is the answer because 3 is less than 5. Our guidelines are giving us the value 5, but here in the expression you can directly see that we have NOR expression. Okay, for NOR expression we need only one NOR gate. Then for this OR operation we need two NOR gates. So total three NOR gates are required. That's it. So the minimum number of NOR gates required, that will be 3. None of the option is correct. Is this clear? So for this question, no option is correct. No option is actually correct. Okay, you can easily see, look at this circuit. This circuit is giving you the function f. This circuit is realizing the function f with help of three two input NOR gates. So remember, no option is correct. But tell me one thing, in the gate exam, if this question you are solving and you are getting the answer 3, but these are the options, then will you leave this question or will you tick one of the options? Don't leave the question, tick this option. Okay, because maybe the question maker is not thinking smart. Yes or no? Maybe the question maker missed it. Because remember, even the question maker, even the IIT professor, even the IIC Bangalore professor, they don't have a systematic procedure, a systematic algorithm, step by step procedure, which can always give you the guarantee of minimum number of NAND gates or NOR gates. Even this Purdue University, the official answer is 5. From the Purdue University, let me show you the official answer. Let me show you what is the official answer. You can see for the fourth part, the official answer is 5. Okay, and remember this circuit that they have created, this circuit Purdue University has created. Some Purdue University professor or TA has created this circuit. This is according to our guidelines. This is our guidelines circuit. Okay, means the professor or the question maker of this question from the Purdue University, they also missed it. Okay, we can do it with 3 NOR gates, but they also missed it. They are saying that answer minimum number of NOR gates required is 5. Okay, and this circuit that they have created, this same circuit we will get if you use our guidelines. I already told you, using our guidelines we will need 5 NOR gates, minimum 5 NOR gates we will need. And you can see here 5 NOR gates. This is the circuit. What I want to tell you, I just want to tell you that in the gate exam, if you are confident that okay, you need 3 NOR gates, means the answer is actually 3, but these are the options, then don't leave the question. Pick this option 5, because you can see among all these options 5 is minimum, right? 5 6 7 8 9. So among all these options 5 is minimum. The actual answer is actually 3, but don't leave this question and tick this option. Okay, I hope you understood this point. Okay, so you can see, if you just look at the expression, if you play smart, then you can easily see that you can get with help of only 3 two input NOR gates, you can implement this function. Okay, so that's it. So this is the complete analysis of this Purdue University question. These are the official answers. You can just check it out. Okay, so that's it, everyone. I hope you enjoyed this session and I hope you learned something new in this session. Okay, so tell me, was this session helpful? Did you learn something new? This wasn't, I can say, very straightforward session. I'm very certain that everyone who is watching this video, who is watching this session, everyone must have learned something new. What do you think? Is there anyone here who thinks that, okay, in this session they did not learn something new? Because I am very sure that these four parts that we have seen, from these four questions, maybe something new you understood. Okay, so please share your feedback. After this session is over, then please put a comment and let me know. Okay, so that's it. We have done the complete analysis. Okay, so remember one thing again, that this Go classes YouTube DPP series, in short, Go DPP series for Gate CS, the playlist link you can find in the description, also in the pinned comment. Check it out. And you can just search on the YouTube Gate CS DPP. This you can search, and you can see here this playlist link is there. Gate CS GOAT DPP series playlist link. This playlist link is there. So just check it out. Okay. And one more thing, that the future of this series, it will depend on your support. So you can see your support decide the future of this series. So please share with all the GATE aspirants. Please put a comment. Please let me know your feedback. Did you learn something new? You want me to continue like that? Basically, just you know you participate. If you show interest, if you encourage us, if you participate, if you share with the GATE aspirants, then we will keep bringing new and unseen standard questions to solve. All these questions will be of GATE CS syllabus. No question will be beyond the GATE CS level. All will be within the GATE CS syllabus, within the GATE CS level. Okay, you can see. So thank you everyone. Please share with the all the GATE aspirants. Please let them know. Please let everyone know that this series is ongoing, and this is a practice series. You can see standard questions practice series every day. We are solving 5 questions with complete analysis. So thank you everyone. Okay. And a student is asking, is this series subject wise? No, we will mix. So just one more DPP we will take on digital logic. Then we will take, maybe theory of computation, maybe discrete mathematics, maybe DBMS. So we will mix. Okay, it will not happen that one subject is going for 15-20 days. No, we will mix the subjects. Okay, so you just keep following, you keep supporting, you keep participating, you keep sharing with the GATE aspirants. This is my responsibility. I will mix the subjects. Okay, maybe in the next, after tomorrow, we can start, maybe for 4 or 5 days we can start discrete mathematics. Then for 4 or 5 days we can start theory of computation. Then for 4 or 5 days we can start DBMS, like that. Okay, then computer organization, then compiler design. Okay, we will do some kind of round robin. In operating system you study round robin scheduling. That kind of round robin scheduling we will do. We can provide every subject, we can provide a quanta, quantum. In the round robin there is the concept of quanta, right? Quanta or quantum. So we can provide a quantum of 4 to every subject, and then round robin fashion we will continue this series. Okay, so thank you everyone. Thank you so much. See you tomorrow. Please share with all the GATE aspirants, and please put a comment. Please let me know your feedback. Did you learn something new? Was this session helpful? Just let me know. Okay, I'm putting my best efforts to bring some questions from which you can learn something, from which you can improve your understanding, improve your GATE preparation. Okay, I'm finding these questions. It takes time. It's not very easy to find these questions. It's really complicated, but I'm finding these questions, bringing to you, providing you the complete analysis. So just please show your support.